So welcome to section 2. This is the section on design controls, and here we're going to cover design controls, design traceability and risk management. As we alluded to in our earlier section and lessons, our risk management processes live inside our design and development processes. And this is of course necessary because the principles of risk management are built on the foundation of design controls, systems engineering principles, and design traceability. And a good way to conceptualize this is as a bit of a pyramid. We have risk management at the top, and we have design controls and systems engineering at the bottom. As a company, how we implement design controls and systems engineering, we should clarify in our design and development procedure. The other thing just to be aware of is that often gets called in ISO 13485, it's product realization. Okay, but generally it's more so just considered design and development. The key elements of design controls and traceability are often conceptualized in the V model diagram below. So here we have this V model diagram, and this will give you an overview basically of design and development, how you're meant to conduct it. And where you're meant to start is intended use. This is just a statement of what the product is intended to do. From our intended use, we'll draft what are called user needs statements. These are basically subjective statements that describe the needs of the user as opposed to the solution that's offered by the product. The next step is requirements. Requirements differ from user needs in that they describe what the product is required to do, or often what the product shall do. And requirements are also different in the fact that they should be objectively verifiable, typically by a test or some other prescribed means, maybe inspection. The line between user needs and requirements is often the line between subjectivity and objectivity. Requirements are also normally drafted at the same time as architecture. Architecture is where you decompose your product basically into a block diagram, and you break it down into what I will call items, but other people often call modules or components. Each component is just a different part of the product, and you have a good bit of artistic freedom in what you end up calling items or modules. From your requirements in architecture, implement the design process. If you're an electronic engineer, that could be writing schematics, doing calculations, doing simulations. If you're a developer, that could be writing code, and that should produce design outputs. Okay, that is the result of a design effort, and that can be things like you wrote the code that produced the source code files and the executable code files, or you drew out the schematic, you selected your components in the design process, resulting in the design outputs of your bill of materials for your PCB assembly and your PCB Gerber files or any schematic drawings, etc., etc. Design outputs can also be details of the different components in your architecture. Once we have those, we have the design outputs. We can now build prototypes if our device is a physical device. And after that, then, now that we've built it, we can test it. There's two types of testing. Verification. Now, I should say here that verification, it doesn't specifically mean testing. Verification really is just objective evidence that the product meets its requirements. So it doesn't have to be testing, but testing is the best form of verification. It's where you have things like your design verification testing. Some people will also consider things like design reviews to be a type of verification. Static code analysis can be a type of verification. Or sorry, I made a mistake there. It's just evidence that you've met requirements, not user needs. Our next type of testing is validation testing. And it's validation that is evidence that you have met your user needs and or your intended use. And typically what validation ends up becoming is things like clinical testing, clinical trials. It can be preclinical testing like animal testing. It can be usability testing, simulated use testing, etc. And it has a more subjective nature than the objective verification testing. Here, say, it could be something like a requirement for a pulse generator is it shall output 200 volts plus or minus 20 volts, and then we'll test the AED with an oscilloscope and whatnot to verify it actually produces the correct pulse that was defined in the requirements. But that requirement doesn't actually provide evidence that the defibrillator can actually be used to defibrillate a person's heart. But what will show us evidence of that will be validation testing, such as clinical trials, for instance. And once we've stepped through all this, we'll arrive at our medical device. And as you can see by the nature of this diagram, it is in the shape of a V, hence it gets called the V model. Verification is evidence that you've met requirements, so this is evidence. And validation is evidence that you've met the intended use and the user needs. So that largely is considered design controls. Now, the question that you might have is how exactly does risk management intertwine with this entire process of design controls? And risk management basically exists over here to the left, When we look at risk management, we take certain inputs like our intended use. We'll also look at the requirements. We'll ask, are they adequate? That could be a risk. We'll look at the architecture. We'll also look at our design outputs because there'll be failure modes associated with design outputs. And from that, generally what we will do is we will implement risk control measures and that basically act as requirements. And it's important that we intertwine it this way because when we introduce risk control measures, we want evidence that they are in fact implemented and effective. So once we introduce a risk control measure as a requirement, we will have evidence it's implemented in both the requirement and the associated design outputs, and we'll also have evidence it's effective through the testing that we perform up here in verification and validation. And hopefully, as a result of that, you can see how design controls and systems engineering is very much so the foundation that risk management is built on top of. The last thing that we'll discuss here is this term, it's traceability. It doesn't actually come from ISO 14971. Its definition is laid out in IEC 62304, which is the software development standard. And traceability is defined as the degree to which a relationship can be established between two or more outputs or elements of the development process. What is meant by that is that we basically give everything a unique ID. And one possible scheme that you can do here is each user need, you should have a bunch of different user need statements. The user needs the device to be safe. The user needs to easily and quickly provide treatment to the patient in an emergency situation, whatever they are for your own device. Every single one, you'll give a unique ID, UN0, UN1, UN2, UN3, so on and so forth. And you do the same for all the other elements. So product requirements, you could go DI1, DI2 for design inputs, or you could just go PR1, PR0, PR1. Software requirements, you go SR, whatever, 1, 2, 3, 4, 5. Risk management, we also want to be able to trace our risk to requirements through to verification validation. So often people will go like risk, I'm going to put down just I'll keep it risk one, but you know you can have risk one, risk two, risk three. You'll also have your risk control measures, maybe RC 1, 2, 3, 4. And once you get over here, you might have verification. It might be test cases, test 0, 1, 2, 3, 4. So it might be requirement P or 0 is verified by several tests. It's verified by test 0 and test 1 and test 2. When it comes to validation testing, it's more so like reports. So you might have a report and you just give it a title or a document code, and it might be report 0 or it might be something else. Similar thing with verification, you can have like your compliance safety test report that proves your product meets IEC 60601 will often act as verification for the requirement the product shall be designed to meet IEC 60601. Therefore, you want to trace that requirement not to a test case but to the actual document. The reason that all this exists is because the system must be made auditable. That is why design traceability is a big deal. There are, of course, also other reasons. Reason number two is it just gives engineers and developers clarity where requirements or tests come from. That, of course, is important because once you separate user needs from requirements, you can now look at requirements and ask the question, do they adequately serve user needs? So that is design traceability in a nutshell, and design controls and system engineering. And I think I'll conclude this lesson here, and I shall see you in the next.